we're going to be starting polynomials, solving polynomials. And you did that back in Algebra 2. That's that plus or minus p over q stuff from Algebra 2 that you did. One way to help eliminate the number of choices is to use what we call a P&I chart, Descartes' law of signs. And a P&I chart is basically used to help identify the roots of a polynomial that are positive, negative, or imaginary. To create them, we use these directions down below, which I'll let you go ahead and read, but we're just going to go ahead and start it. So pause it, and then go ahead and take a look at how we do these. It's very simple. Now the only difference is this should be p of negative x. So we have to fix that. So what we're going to do first off is we're going to count basically in the positive x the number of sign changes here. And if you notice, there's 1, 2 sign changes. And then what we're going to do is find p of negative x. Now that's very easy. If you plug in a negative, the odds change signs. Negative 5x cubed, the evens stay the same. 8x squared plus 4x plus 3. And again, I count the number of sign changes. And in this case, there's only 1. Next, we generate our P&I chart. P for positive, N for negative, I for imaginary. And I always like to put over here, off to the side here, the degree. Now, the degree for each of these always has to be 3. So the degree has to be 3 there. We'll talk about that in just a few moments. Now, if I look at the positive changes, there were 2. So that means there could be 2 or there could be 0. And that's what the directions up here above said. We're going to subtract 2 every time. So if there's 2, I subtract 2, I get 0. So that means there could be either 2 or 0 positive roots to this polynomial. The negatives, now there's only 1 negative. So I'm going to put a 1 here. Now, if there's only 1, there has to be only 1 negative every time. So I'm going to carry that 1 through. And the reason for that is I can't subtract 2 from 1. Next, I find out how many imaginaries. Now, the degree always has to be 3. So I have 2 positive, 1 negative. It has to be 3 roots, or let's call that roots, I guess. Might be better to use it. I have 2 positive, 1 negative. That means there can't be any imaginary. Now, but what if we had the 0 positive? That means we'd have 1 negative, and there'd have to be 2 imaginary. So again, it's going to add up to be 3. Very easy to do. Let's take a look at the next one here. So this is my positive, because x is positive, so I count the number of sign changes. There's 1, negative, nope, 2. So there are 2 sign changes. And then I find p of negative x. P of negative x, anything with a negative changes, so negative x to the 5th. This is even, so it stays the same. Odd, so it's going to change. Even stays the same. Odd changes plus 1. And again, I'm going to count the number of sign changes here. And there's 1, 2, 3. So there are 3 sign changes there. And then I do my P&I chart. P, N, I. And again, I like to make my other one is the number of roots. Now in this case, the number of roots always has to be 5. That's the degree. That's that 5. And that is the number of roots that we have to have. So they have to add up to be 5 when we add them all up. So let's deal with the positives. I can have 2 positives. So if I have 2 positives, let's deal with the negatives. Well, I could have 3 negatives, or subtract 2, I could have 1 negative. So now, if I have 2 positive, 3 negatives, that means there's going to be 0 imaginary, because remember, 2 plus 3 is equal to 5. Now, what if there are 2 positives and 1 negative? See, now I'm dealing only with the positive first. Now, in this case, I have 2 positive, 1 negative, Well, it has to add up to be 5, so what do we put in here? There must be 2 imaginaries. Now, that deals with the p is 2, but remember, we have to subtract 2 from it, so I could also have 0 positive. Now, if I have 0 positives, I could have still 3 negatives. I can still have 3 negatives, or 1 negative. Now, if there are 3 negatives, 0 positives, that means to be 5, I have to have 2 imaginaries. But if I have 0 positives, 1 negative, that means we can have at most 4 imaginaries because the sum has to be 5. Now, basically what this helps us to do is it's going to help us eliminate choices later on. So basically it's saying we could have 2 positives, 3 negative roots. We can have 2 positive, 1 negative, 2 imaginary roots. We can have no positives, 3 negatives, and 2 imaginaries. Or we could have 0 positive, 1 negative, and 4 imaginaries. It just takes care of all the types of combinations of roots we can have here. All right. What I would like you to try to do is number 3. Just try to do number 3. We will go over this in class tomorrow. It is very challenging to learn this at first, but once you learn it, the pattern is pretty easy to do. So go ahead and try number 3, and we'll take a look at that tomorrow. All right. What we're going to talk about next is kind of a little bit more to deal with the synthetic division, how we can use synthetic division, applications of synthetic division here. We've given here a synthetic division chart. My polynomial up top here, there's my polynomial, and my possible roots, what we're dividing by, are possible roots that we're guessing. Now, the first question they're asking us is, what is the function that's being divided? Well, if we remember anything from our synthetic division, right? The part that we're dividing is the top part. That's the polynomial. Don't make that negative. So I write it out. 2, negative 7, 2, 14, negative 12. And what I'm going to do is I'm going to put the x's. We start off with x to the 0. I go backwards. X to the first. Put a plus there. X squared. X cubed. And then here x to the 4th. Very easy to do. I start backwards, makes it a little bit easier. And that's what our polynomial is equal to. Now, the next question is there a root? Well, this is our factor theorem from the other day. And for the factor theorem, we say that the remainder must equal 0. So where do we get the remainder on our chart? The last column. These are the remainders. What that basically means is if I divided by negative 4, my remainder was 924. So I look, is there anywhere where my remainder is 0? Yes, right here. That tells me that this right here is a factor, therefore we have a root. And where is it at? Located? It's at x equals 2. So yes, there is a root at x equals 2, and that is because the remainder equals 0. And there's our answer. Easy to do. All right, the next question says, what's the y-intercept? Well, we should know that one. That is f of 0, where x is 0. So I take a look here. Where is my y-intercept? Here's where x equals 0. So my y-intercept, go all the way over here. It's the remainder. See, what we're using here is our remainder theorem. And recall that the remainder theorem says that the value of a function is the remainder. So if I want to find f of 0, what I'm going to do, here's f of 0. I go all the way over here. There's my remainder for f of 0. There's our remainder for f of 0. So what does that tell me? F of 0 is negative 12. There's our y-intercept. Now, 4 is the exact same type of problem. We are using our remainder theorem. So for the first one, if I want to find p of negative 3, there's negative 3. What is it equal to? 315. And that's what I'm going to put here, 315. Take a minute. Find P of 3. Ah, there it is. There's 3. What's the remainder? 21. So what's the value? 21. Very easy to do. Now the next question, number 5, is going to lead us into what we're going to talk about next. How can we show that there is a root between x equals negative 2 and x equals negative 1? So take a look at the graph. Between x equals negative 2 and negative 1, how can we show that there is a root? Look at their values. At negative 2, the value is positive 56. At negative 1, the value is negative 15. We're going from a positive to a negative. You can't do that without crossing 0. And our definition of a root, it has to equal 0. And that's what we're going to say here. Because f of negative 2 equals positive 56 and f of negative 1 equals negative 12, there must exist a root. There must exist a root, because you can't go from a positive to a negative without crossing 0. Now, we have a special name for that. It is called the intermediate value theorem. And we're going to talk about that in part 2. So make sure you look at part 2.